real exam questions. This is question 51 about slab design. Prove that the effective depth of a slab at which the main reinforcement just yields is given by 69 point the square root out of the bending moment divided by the concrete quality. This formula is valid with dimensions d in millimeter, m in kilonewton meter per meter, and FCK in megapascal. What is the practical use of this formula? When do you use it? First, we look at the strain diagram with on the right-hand side the concrete strain. On the left, we have the steel strain with effective depth D and a total depth of H. We are in region simple bending, so in region 2A, we have two limits in that region, and we are looking for yielding of the steel, just yielding of the steel. So when we look at the stress in the steel, it builds up until it reaches FYD, until it yields. So in this point, that's the strain diagram that we want to find. That's just before leading, just there, before yielding. So we are in domain 2A for yielding of steel. Look at the concrete section. Let's draw the strain diagram. This is the concrete strain, and this is the steel strain. The effective depth is D, and the neutral axis is indicated here. And when we look now at the stresses, then we see that this is the concrete stress. We are in domain 2A, so parabol and rectangle is fully developed. And then the lever arm Z is between the concrete force, concrete compressive force, and the steel tension force. And of course, this is the position of the neutral axis is X. In domain 2A, we know then that the filling coefficient is constant and is 0.81, and that the position of the concrete compressive strength is delta Gx, and delta G is 0.416. Epsilon C on top is maximum, so it's 3.5 per mil. The strain in the steel now is easy, just yielding. That means that we got the characteristic value divided by the material factor times, and divided by the modulus of elasticity of the steel. It gives you 2.174 per mil. The C is of course X over D, which gives you the position of the neutral axis. It is of course 3.5 divided by the sum of those two, because then you are working in this triangle. And with those elements, we can have a rotation equilibrium around the tensile stress in the reinforcement of the point of where the total tensile force of the concrete is. From there on, fill in the different values, and we see that we have μd, a reduced bending moment of 0.371. But the definition of a reduced bending moment is equal to bending moment divided by BD squared FCD. And we will write this equation with MD in kilonewton meter per meter, B the width in millimeter, D in millimeter, and FCD in megapascal. So FCD is 0.85 times concrete quality divided by the material factor, and it's then equal to 17/30 of FCK, the characteristic value of the concrete compressive strength. So now we know that μd was 0.371. That's what we want to achieve. Then we fill in the different values on the right-hand side. And you see that you can, from this equation, because μd is fixed, you can take d out of this equation, and you put it in the right dimensions. So you have to multiply here by 10 to the power 6, and d is 1000 millimeter. And simplifying this, you have this equation. So this equation, it's in fact, it's the design formula, gives you the slab with the smallest depth possible and avoiding brittle failure. So you cannot go less large than this value D. That's the limit. If D is getting bigger, then the reinforcement will not yield, and you will have a risk of brittle failure. Of course, MD is in kilonewton meter per meter, and FCK is in megapascal. This type of dimension formula is used to, for instance, maximize a clearance below the slab.